Hello, everyone. All right, let's try solving problem 2C, 2, and 2E, which is basically true or false on the definition of big O, big omega, and big theta. All right, so 2C, it asks a question, if a function is omega of n, then it could be also in O of n squared. Now, remember that in class, we talked about how code can be modeled using a function, right? This is what code model is. Right? So we can talk about the performance of the code using a function, right? And basically, we also talked about how omega is the lower bound of that function, and O is basically the upper bound of that function. And so let's kind of like break this question down into part by part, right? So first question we should ask is, if a function is omega of n, right? What does that mean? Well, omega of n means that a function can grow as fast or faster than n, right? So that means that our code's function can be either n squared, n cubed, and so forth, right? Because omega of n is basically our lower bound in this case, right? And what does it mean to be O of n squared for our function? Well, if omega is basically the lower bound, then O is basically the upper bound, and it basically means that the function will grow as slow or slower than n squared, right? So if I didn't know anything about omega, and for like let's just talk about like let's say we didn't know anything about omega of n, and we only knew about O of n squared. Well, if O of n squared is basically the upper bound, then we can think about like the vice versa of omega, and in the sense that our function can be either n squared, n, and so forth. And so to answer this question, if a function of omega then it could also be O of n squared. It is actually true in this case. And let's kind of visually think about this. So if a function of omega of n squared, right, it's basically this whole entire line, this whole entire lower bound, right? And it basically tells us that our function can be either, like, our function can grow as fast or faster than n. So that means that it could either be n log n, or n squared, n cubed, or and so forth on. Okay. And basically O of n squared is basically this upper bound. And because it is basically within this whole entire shaded region of omega of n, like we can see that this n squared is basically contained within this shaded region. And when we actually have set a boundary of O of n squared, we can also see that this whole entire shaded region is also contained in this orange region. If a function is, if a function is theta of n, then it could also be O n squared, right? And so, what does theta of n mean for our function? The function is tightly bounded by n, right? So we also talked about this definition of theta of n, and theta of n basically tells us that if we're given a tight O and its n, and if we're given a tight omega and its n, then we can definitely say that is theta of n in this case. Right? So it basically tells us that my code will run exactly at runtime of n, essentially, because I knew that my tight O and tight omega is n in this case. Right? And and it says, what does O of n squared mean for a function? Well, it's the same definition as before. It basically says that the function will grow as slow or slower than n squared. And to answer this, this is actually true, right? So here we talked about how theta of n kind of describes a tight bound in this case, right? So in this case, this describes this tight bound, but however, O of n squared could be non-tight bound, right? So what this means is that we know that n squared dominates over n in terms of complexity growth, right? So it is true that I can technically say, if I had a code that is basically that runs in O of n, then I can technically say that my code also runs in O of n squared too, right? And this is true because this describes the tight bound, but this doesn't describe the tight bound, right? And because of this, we can definitely say that if a function is theta of n, then it could also be O of n squared, because we're basically describing the non-tight bound in this case. And so this brings up the question: why are tight bounds important in the first place? When we can just say like, well, in this case, like, why is theta bound even important in this case? Like, why are tight bounds even important in the first place? Well, let's kind of talk about this in terms of scenario. Let's say you had a boss, right? This is your boss, right? This guy right here, and let's say this is you, right? With your fancy computer, right? And you have this code, right? This code public void method. And for our purpose, let's just say our code ran in, upper bound of O log. Right? You went through this, and you came up with the analysis that this whole entire code ran in, I guess, theta of log n in this case. Okay? And so that means that this is O of log n, and this is also omega of log n. In terms of and they're remember that these are both tight bounds. Okay, and your boss says, "Hey, I want you to tell me how fast this code is, or I guess the performance of this code. Like what is the bound essentially? Because he wants to know like how efficient your code is, right? And the correct way of saying is that like this tight bound is like theta of log n, but you could technically say, oh, because I know that my function is also O of log n, then it is technically true that I could also say that it's O of n, or O of n squared, or O of n cubed, because these are all like non-tight bounds, right? And you could technically say this, but this is not really accurate in terms of how in terms of efficiency of your code. Right? So when we're talking about like I guess like we want to give out like the tight bounds in this case, right? When we're talking about code performance. So I guess since I talked about why tight bounds are important, let's move on to 2e. And 2e basically says it will ask if a function is omega of n, then it is also O of n. It is all like so. This is like a tricky problem. It says it is always n O of n, right? And so let's kind of break this question into different parts. What does omega of n mean for our function? It means that function will grow as fast or faster than n. And what does O of n mean for our function? Well, the function will grow as slow or slower than n because it is the upper bound, right? And this is actually false, right? And this is false because this question asks if a function is omega of n, then it is always n, O of n, right? So we saw that in this graph that if our lower bound is omega of n, right, then it includes this whole entire orange region, right? And that means that we can't just based on this whole entire region, we can't just say, well, this based on this omega of n, like it has to be always this n squared function growth, right? We can't determine that. Like this is not true. It could technically be it could be also n squared, or n cubed, and so forth on, right? This is our lower bound, right? It's a bound basically, right? And so because of that, it is false in that case. And so I guess one thing I want to talk about, or kind of briefly mention, is that remember that omega is the lower bound, right? But this is not equivalent to worst case. right? This is a common misconception, and it's the same thing, right? O is basically the upper bound, and this does not mean best case. We're actually this should be worst case, and then this should be best case, right? And so 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 um sorry. So based on the case, right? Either it is best case or worst, then we can determine its O, omega, and theta. And also based on its case, best case, we can also determine its O, omega, and theta. And yeah.